So this is the problem that I'm calling Problem 3MM, which is problem 3 with the Michaelis-Menten. Michaelis-Menten non-homogeneous, nonlinear consumption as compared to the linear, which we had, which was problem 1 revised. And in this, we actually have, I think, a problem that winds up being solvable. The process of stepping through it, you'll see, is very similar to all the other problems I've uploaded. So when we do this, the notation, I'm going to have a C sub I for the concentration of the interior. This is where the cells are, and that ranges from 0 to R sub 1. And concentration CE for concentration of the exterior, and that ranges from 1 to R2. Generically, I'll write CX, where X can be either I or E, since sometimes we'll have uniform relations. Our problem solution is going to look like this. On the exterior, we have a constant. We have a constant concentration. At the interior, we have no flux, which means that the slope at R equals 0 is 0. At the boundary between the interior and exterior, we say that the concentrations must be equal, so it has to be a continuous distribution, and we're calling that C1, and the surface here, we're calling that C sub 2 because it's at R2, and C1 at R1. And this only leaves us with 3 boundary conditions, and of course we're going to need a fourth one. And the fourth boundary is that we're in equilibrium, and because we're in equilibrium, it means the flux of mass going in and going out have to be equal, which means that well, the flux has to be equal. And we know from Fick's first law that you can write the flux as the slope of the concentration times the diffusion. So we're saying that at R1, the slope of the interior with respect to R times the diffusion coefficient of the interior must be equal to the slope of the exterior concentration with respect to R times the diffusion coefficient of the exterior. So that's D sub I times dCi dr is equal to D sub E dCe by dr at R is equal to R1. So this is the setup, and again we start with zoom in here a little bit, I think. Start out with Fick's second law. This is for the interior, and in the interior we have this consumption term, which is the Michaelis-Menten expression with V sub m and K sub m. And then we have our 2 boundaries saying that at R is equal to R1, we have concentration C1, and then we have that at R equals R0, the slope is 0, because we have no flux to the interior. And because we're working for the steady state solution, we can take that derivative with respect to time and set it equal to 0, which gives us an expression that looks like this. This is our differential. Notice we went from being a partial differential equation to a total differential because we only have one variable now. Then we can go to the external problem, and we have the same except no consumption term, and we have constant values at the boundaries. And this can then be written in radial coordinates like this. So that is our differential equation. Next step, we're going to convert to dimensionless units, and just as in the previous videos, we're going to use rho for dimensionless position, chi as dimensionless concentration. In this case, chi is going to be chi sub I or chi sub E, nu as dimensionless Michaelis-Menten saturation consumption, and kappa as the 1/2 saturation concentration, the non-dimensionless Michaelis-Menten expression. And then kind of over the course of this next set of equations, we're solving for the individual terms that go into our ordinary differential equations here, equations 4 and equations 8. So doing that, here is one solution, equation 14, equation 15, equation 16, equation 17, and here is equation 18. And taking those together, we're now able to write the differential equations here. This is the interior differential equation, and we've got a bunch of cancellation. And these are our boundary conditions. So Ci at R is equal to R1 is equal to C1, which allows us to write chi I at rho is equal to R1 over R2, because we defined our dimensionless length as ranging from 0 to 1 on the exterior. So the boundary between the interior and exterior occurs at R1 divided by R2. That gives us chi I is equal to C1 over C2 as the boundary condition. And then here we have the derivative of concentration interior is equal to 0. With appropriate substitution, that gives us that the derivative of chi sub I with respect to rho at rho equals 0 is equal to 0. So that's the interior problem. And the exterior problem then is this. Again, a bunch of cancellation, giving us this ordinary differential equation. Same boundary again, and you'll see that's redundancy. And then at the surface, chi sub E at rho equals 1 is equal to 1. So this is how we've non-dimensionalized our equations. And the problem is that the ordinary differential equations, say equation 19 and 22, we have this 1 over rho in it, and because of that, it's a non-linear differential, and we want to linearize that. And the way you linearize that problem is making the substitution u sub x as a function of rho is equal to rho times chi sub x, a function of rho. And this substitution is going to simplify our problem. So let's step through the substitutions we make. So these are again chi sub x, so they're kind of a uniform expression. So this gives us a derivative of chi with respect to rho, and converting that to u sub x is that. And then we can take the second derivative, and taking the second derivative is the derivative of the first derivative. This whole thing expands out using chain rule, which is hairy, but it's just a bunch of accounting. It's nothing too challenging. So this is the second derivative of chi with respect to rho written in terms of u. Substituting those into our ordinary differential equation, we get something that looks like this. And expanding this out, we get this equation, and we have all of this cancellation, which ultimately gives us a differential equation that looks like this. So this is our ordinary differential equation for the interior. And then the boundary conditions, converting from chi to u, will give us this. So u sub I at rho is equal to r1 over r2 is equal to r1 over r2 c1 over c2. And then the other boundary condition, the derivative, well, substituting in for the derivatives, taking this, and recognizing that we're interested in the case where rho is equal to 0, and we've got a 1 over rho there, which becomes rho equal to 0. We now have ui at rho equals 0 is equal to 0. So now our boundaries are not in terms of derivatives, but just in terms of values. So that gives us two boundaries for the interior problem, and the exterior problem behaves in a very similar fashion. Again, you take and you expand out your substitution, you get a bunch of cancellation, which is great, and this is our ordinary differential equation that we have to solve. It's just the second derivative of u sub e with respect to rho equals 0. And now our boundary conditions, here's 1, ue at rho is equal to r1 over r2 is equal to r1 over r2 c1 over c2. And then the second boundary is that u sub e at rho equals 1 is equal to 1. Well, of course, this is a redundancy, and because it's a redundancy, we're actually missing a boundary condition, and our boundary condition we're going to use then is that the flux on the left and the right hand side of the interface between the interior and exterior have to be equal. So making substitutions, here the derivative of c with respect to r in the interior, and ce with respect to rho. Oh, is that rho or r? That's r, sorry. But you'll see it comes out, though, they're the same. You wind up with this expression. Again, lots of cancellation. And this is our expression. Converting from chi to u, we make the substitution. And this is the boundary we have. So, this is the punchline. This is our final problem we have to solve. Zoom out so you can see it all in one shot. That's it. So the first differential equation is a differential equation for the interior, which has a consumption term. That's a minus nu u sub I over kappa plus u sub I rho to the minus 1. And then our second is just the exterior, which is just the second derivative of u sub e with respect to rho. And then we have 4 boundary conditions. We've got that in the far interior at rho equals 0, u sub I is equal to 0, u sub e at the exterior boundary, rho equals 1, it's equal to 1. And then we have that u sub I and u sub e must be equal to each other at rho is equal to r1 over r2. And not only are they equal to each other, but they're equal to the ratio of c1 over c2. And that's how we non-dimensionalized our problem. And then we have the boundary condition saying that the flux must be equal at rho is equal to R1 over R2. And if you look at this, you'll see that this looks very similar to previous problems we solved, and in particular, you can imagine how this would be solved using the shooting method. And I've stepped through that, and we'll come to that in the next video.